Yeah, yeah, sure. Yeah, yeah. I have a couple of announcements. First of all, it's important for departure. So you will find posted on green panels two lists: departure on Friday and departure on Saturday. We will try to combine buses and cars. So please leave your name on corresponding list, but also leave flight hour. It's very important that we can group people into clusters and send them according to leaving time. So another thing I would like to announce for participants of EBP, only because Clay people already heard this. In your backpacks, you already found a gift to us from Elsevier Publishing. It's a pen drive which contains volume dedicated to Professor Kiyoshi Ito. It was volume which was made, the idea came soon after his sad news of his death, and Mark Yor and Maria Eulalia Vares were invited editors of this volume, and it contains 4 articles by prominent French mathematicians and colleagues and collaborators of Ito from Japan. So you find this on your pen drive, this volume. So that was a gift from Elsevier. And now I give driving wheel to Frank. In the first lecture, at the end, you saw 2 very simple examples of polymer chains, both polymer chains in a sense without interaction. There was the simple random walk, which was the most simple polymer you could possibly imagine. You consider all possible lattice paths, and there is no energy associated to a lattice paths, so that the probability distribution on the set of lattice paths was completely uniform. And you saw also the self-avoiding walk, which is an example that you obtain by putting a geometric constraint on your set of lattice paths. You don't allow any self-intersections. And apart from that, there is also no energy associated to every path, so that you again get, as a random polymer law, a uniform distribution on the set of all self-avoiding paths. The second model you could also interpret by saying allow all paths, but give an infinite energy to every path that has one or more self-intersections, and then the path measure, the Gibbs measure, will immediately throw those out because they get weight 0. What I'm going to do in this lecture is talk about a model where you again have a set of paths, and we will be looking at 2 different examples, and I will assign a non-trivial energy to the path this time, and there will be a mix of both attractive and repulsive interactions. So there will be something where you say, if you self-intersect, well, that's not forbidden, but it comes nevertheless with a penalty. And on the other hand, I will give the path a reward when it touches itself. And so I will explain that in detail in a second. Now, this is a model that you can think of as describing a polymer that lives in what you would call a poor solvent. It's living in something in which it doesn't like to be dissolved. So this polymer cannot self-intersect because it sits in its own way. And so we're going to say, okay, if you come close to yourself, you're going to get a penalty for doing that. On the other hand, the polymer does try to touch itself as much as often, because if it does that, it pushes out the bad solvent, which it doesn't like to meet. So a polymer that sort of touches itself will not allow its bad environment to get in its way. And we will see that in this model already there is quite some interesting behavior going to go on. So we're going to have a penalty. Let me write penalty for self-intersections. There is going to be a reward for self-touchings. And so this interaction, this part is repelling, and this part is attracting, and it will be the mix of these two things that will make this model interesting. And we will see that there will be three phases. So depending on the choice of parameters with which I weigh these things, and I will write down an explicit model in a second, there will be three phases. There will be a phase that is called extended. There will be a phase that we will call collapsed, and there will be a phase that we will call localized. And the picture that I want you to have in mind for these three phases is in that this phase, the polymer will sort of look rather sort of trying to avoid itself. Here, it will be sort of collapsed, but not, it will still have a certain spatial extension, whereas in this case, the attraction is so overwhelming that the polymer is basically going to live in a finite set of the space. So you could think of this as a kind of super collapsed version. And so in this case, it is sort of like a random coil. It's something that sort of winds around in space and is covering quite a bit of space. Here it is getting a bit more localized, and in the third phase it will be sort of really totally collapsing in on itself. So this is the kind of thing that we're going to try and be after to describe. Now, this kind of behavior is seen in experiments. For instance, if you take polystyrene, which is a synthetic polymer, and you try to dissolve it in cyclohexane, then there is something happening of that nature when you are somewhere between 30 and 35 degrees Celsius. So if the temperature is above 35 degrees Celsius, then somehow this polystyrene is dissolving well in cyclohexane, so it has a kind of extended, it will be in something like an extended phase. But the moment you lower the temperature, it starts to dislike the cyclohexane so much that it wants to push the solvent away, and what will happen is that it will collapse to something that looks something like the middle. Now, the localized phase is something that, in this case, you don't see because the polymer cannot sort of really go into a finite piece of space, but you will see this phase transition nevertheless happening. So, and you can really measure this, that as a function of the temperature, as you change the temperature, you are changing the interaction strength, that you see this thing really sort of collapsing in on itself. And that's the kind of thing that we're going to try and model. There will be 3 parts to this lecture. I'm first going to talk about an undirected model. So a model where the path doesn't have to go into any particular direction. And we will be able to say a few things about the phase transition. In particular, we will be able to see the phase transition between the second and the third phase. But it will be quite hard to say more. The mathematics at present stops there. And in order to get our hands on the phase transition between the first and the second, I will turn to a directed model. So I will make a severe restriction on the number of paths that the polymer can take. And this restriction allows us to make progress because we are looking at more simple configurations. It's a bit like what Gordon was explaining this morning. If you go to half planes or bridges, there's something nice in the structure that will allow you combinatorially to make progress. And then in the third part of the talk, I will mention a result that Dima Joffe talked about last night already. And this is what happens when you have a collapsed polymer. So because of attractive interactions, it collapses on itself. What happens when I take the endpoints of the polymer and I start to pull on it? So can I sort of decollapse the polymer as I pull at its endpoints? And there has been wonderful progress, and I will come back to that at the end. So here is what a collapsed polymer would look like. You could imagine you have some sort of long string of monomers, and these things can, well, they cannot sit in each other's space, so there's some kind of repulsion going on because of that steric hindrance. And at the same time, there can be attractive forces, either because there are attractive forces between the monomers, for instance, van der Waals forces, but they are very weak. But we think of a model where this says, you know, this thing is living in a solvent that it doesn't like, and it's going to fold up in a way just to push out the solvent. Okay, I'm going to start with the first of the 2 versions of this model that I want to tell you about. First, we start with an undirected model. So imagine you allow as your set of paths all possible lattice paths of a certain length, n. So there are no geometric restrictions. I'm going to write down a formula in a second. And here, for instance, you follow the path, and it goes like this, right? And you say, well, there are 2 self-intersections happening here. So I take note of the fact that on this path here, there are 2 self-intersections, which are indicated by crosses. And the path is also 4 times touching itself. So here, it comes close to itself. It's a neighbor of an earlier point. And if I go along, I will see that on this path, there are 4 self-touchings. So for every path that I draw in my lattice, I can count how many self-intersections there are and how many self-touchings there are. And in the model, what I want is the self-intersections, I want to give them a penalty, because a polymer doesn't like to sit in a space that it has already occupied. But I'd like to give a reward to the self-touchings, because once you have a self-touching, there's no room for your poor solvent to be sitting here. So this is, of course, a very mathematical and a way of describing that phenomenon, but it should be a reasonable way to capture the effect of the poor solvent. So let's make this a bit more precise. And so what are we going to do? As I said in the first lecture, each time you want to define a polymer model, you have to first define the set of paths that you're willing to look at, the set of allowed paths of a certain length n. You then have to assign an energy to each of these paths. And once you've done that, you get a Gibbs measure on the set of paths, which you think of as describing as the probability distribution of a random lattice path. So in this case, what we're going to have, Wn, is simply all n-step. Let me write bigger, sorry. All n-step nearest neighbor paths. And I always want them to start at the origin. So that is written here. You look at all paths that start at the origin and that the increments of the path have length 1 in the lattice norm. So there is no geometrical constraint on the set Wn. And then I'm going to have to introduce a Hamiltonian. So for every element of this set of paths, I have to specify what the energy is that I want to associate with this path. And this will have two parameters, beta and gamma. And this will be a difference of two terms, beta times something that depends on the path minus gamma times something else that depends on the path. And In of W will be the number of self-intersections. Okay, so that would be the sum over all I and j running from 0 up to n ordered such that the distance between omega I and omega j is 0. So that is the first part. And then there will be something, and I guess I will move over here. Where is my cloth to clean? Let's see. Where has the eraser gone? Oh, here. And then there will be a part Jn also associated to the path, and this will be the number of self-touchings, which we define as 1 over 2d as the sum again of all ij running from 0 up to n I ordered, but I want I to be even less than j minus 1 of the indicator that the distance between these points is 1. Okay? Now, why am I restricting I to be smaller than j minus 1? That is, I do not want to count self-touchings inside the path, because the path is nearest neighbor, so every successive pair of times there would be a self-touching, but I don't consider those to be self-touching. So this is the number of self-touchings not within the path. Okay. And I'm also sticking in a factor 1 over 2d here, just as a convenient parameterization, because every site has 2d potential sites as neighbors, and I want to discount that by 1 over 2d, just for convenience. And there will be then in the Hamiltonian 2 weight parameters, beta and gamma, and I will be interested in making them both positive. So these are parameters that we can play with. Okay, so what this is doing, every self-intersection gets a weight plus beta, and every self-touching gets a weight minus gamma. And if you put that in the Gibbs measure, so the Gibbs measure, which will depend on these parameters, would be a normalizing constant, and then, as prescribed, e to the minus beta gamma n of w. Okay, and I'm going to put here as a reference measure this is the law of the n-step simple random walk. So I want to define my Gibbs measure now relative to the law of the simple random walk, because I want to compare it with the simple random walk. But that, of course, is a completely harmless thing to do, because this PNW is anyway the uniform distribution on the set of paths. So this is basically just a constant, 1 over 2d to the power n. But I'd like to put it there, because then I can think of this path measure as a perturbation due to interaction of the random walk that has no interaction energy. Yes? I'm going to draw a conjectured phase diagram in which you will precisely see what we are expecting that will happen as a function of beta and gamma. So indeed, it will be very much a competition between how big beta and gamma are compared to each other, but not always. So so you will see that coming up. Okay, now if I would take gamma is equal to 0, then I'm back at the weakly self-avoiding walk. So then there is no contribution coming from self-touchings, and you will just get a penalty for every self-intersection. And so that falls in the class of weakly self-avoiding walks that we believe, and I think the right word is how Gordon would put it, it's predicted to be in the same universality class for all dimensions as the strictly self-avoiding walk. So we believe that as soon as beta is positive, irrespective of how big it is, the path of a weakly self-avoiding walk will simply, in all respects, behave as if beta would be infinity, but would be very different from what happens when beta is equal to 0, which is the simple random walk. Okay, so roughly at this stage, you would, of course, expect that if beta is going to be very large compared to gamma, then the self-repellence is going to win over the self-attraction, and you would expect that this thing starts to behave like, well, perhaps self-avoiding walk-like behavior, and that it would be quite extended. But on the other hand, if gamma would be large compared to beta, so the opposite case, then the self-touchings are rewarded so much that you are willing to take the self-intersections that typically come with that as a price, and you would expect this whole thing to start to collapse onto itself. And at this point, you would then say, like Leo was already saying, well, for beta somewhere in the neighborhood of gamma, or perhaps of the same order, we expect a phase transition coming up. And the question is, where is this phase transition exactly happening? Okay, I'm going to give you two theorems that are going to talk about one of the two phase transitions, so between let me put that again here. So I had an extended phase. That's what I'm targeting. I mean, I have to explain to you why these things are really there. A collapsed phase and a localized phase. And we will be trying to get a picture of these things as I'm looking in the space in the quarter plane of values of beta and gamma. So what's going to happen in this quadrant? And the first thing that we're going to look at is a transition between this one and these two, where we still are not going to distinguish between these two. And this is what we would call the localization transition. And what I'm going to do for the time being is I'm going to call these two things together inflated. So I will first discuss a distinction between something that I would call localized and something that is inflated. And then later, this part we will subdivide into further phases as we go along. So we're first going to look at a result that describes a transition from something that is completely localized to something that is not localized. And then the part that is not localized, we will subdivide it further in how it is not localized. And here are two theorems that are due to Remco and Achim Klenke from 2001. And they are theorems that talk about this distinction. There is what we would call an inflated phase, which later we will see can be subdivided into further subphases, and a localized phase. And the precise statement is the following. For every integer L, you can look at the L box in your lattice. Okay, so this is a result that applies to any dimension. And here, the first theorem says, let's look at the case where beta is larger than gamma. So this is the case where the repellence is stronger than the attraction. So that should somehow say that this thing doesn't want to really be too collapsed on itself. And then the statement is, for every beta larger than gamma, you can find an epsilon 0, which will depend on beta and gamma, but is positive as soon as beta is larger than gamma, such that if you take any epsilon smaller than this positive epsilon 0, then you can find a number that will still depend on beta and gamma, but also on the choice of epsilon that you pick here, but nevertheless positive, such that there's an exponentially small probability in n for the path of the walk. And here I'm using the notation SI as, so SI I now think of as a random realization of a path that I draw from my set of paths when I draw it according to this Gibbs measure. So yeah, I'm going to do that kind of notation more often. So if I write S, S, which would be S running from 0 up to n. This will be a random sample from the path space according to this Gibbs measure. So then, I said the Gibbs measure makes me think of a random path, and S would be the notation for this random path. Okay, so what this says is that it will be exponentially unlikely in n that the entire path stays folded up in a box of size epsilon times n to the 1 over d. So it will, with a probability 1 minus something very small, simply somewhere stick out of a box of size n to the 1 over d. The second theorem is talking about exactly the opposite case. So what happens when gamma is larger than beta? Then the self-touchings are more rewarded than the self-intersections are penalized. And therefore, you would expect that the self-attraction is somehow winning. And the statement, indeed, it is winning in a very strong way. You can find a number c, which will depend on beta and gamma, which is positive. And you can find an L0, finite, such that for all n lengths of the path and for all large enough L, you will have a very large probability, modulo an exponentially small error term, that you will all stay folded up in a box of size L. So basically, the picture is that there is then a phase diagram. There's already here a line where gamma is beta. In this regime, you will be localized. And so this means that your entire path is folded up into a box that has some finite size L. But if you are on this side, you will be inflated. And you will see that if you take a box of size n to the 1 over d, then you are at some point going to have to stick your nose out of this box. So you cannot, so there's a real change between a very localized behavior and a behavior where you already start to become inflated. Yes? Yeah, that's very important. Yeah, because it was important that I would put that here, otherwise I would have to shift the value of gamma. Basically what happens is that when you are at betas equal to gamma, then, so it's like you would put here beta and here a beta, and the difference of these two functions here can then be sort of written as a somewhat simpler function of the path, in fact, of the local times of the path, using symmetries. I'm being a bit rough about this and vague, but that's what is happening. And therefore, then you can see that that will exactly make things sort of critical. And as we go along, you will see that. Okay, so here is again this phase diagrams, but we'll keep it there because we'll start to add more things to this phase diagram as we go along. So here is then a first indication of something where the path behavior really changes as you cross this line. Now, let me give you a very rough feeling of what is behind these two theorems. What is behind it is some geometry and some combinatorics. And basically what you're going to do is compare weights of paths that you get by sort of taking a path and sort of flipping it in a half line or with respect to a plane. So it's a bit of the type that Gordon was describing when he was talking about the self-affording works, the bridges, the half spaces. But when you do this here, you have to, once you start to fold the path, keep track of how you're changing the energies. So roughly, what happens is that to prove that in the first theorem, when the self-repellence wins from the self-attraction and you get this inflated behavior, you have to prove that if you take epsilon small enough, then if you want to force a path to stay inside a box of size epsilon times n to the 1 over d, so if you try to prove that it is not sticking its head out, then you have to check that the path will have, or at least most paths will have very many self-intersections and very many self-touchings. And for most paths, they will be sort of comparable in number, and then because you give a higher penalty to the self-intersections than to the rewards, that will be a very costly thing to do. So that is the intuition, but to make that all work, you have to do a lot of folding. You take this box and you pick a path and you sort of fold it over and several times try to put it in the box and say, okay, each time I fold over, what energy change does that have? And you have to keep track of that. And that is what is done in the paper, and it would really be a much longer story to explain that to you in detail. But that is basically what is happening. So the second theorem where you have the localized behavior, that basically says, suppose I am in the situation where the self-touchings are winning so the attraction is stronger than the repulsion. Then you have to prove that the minimum of your Hamiltonian can be achieved by some path that stays in some finite box. You can imagine if you start to fold everything into a finite box, there will be many self-intersections and many self-touchings. But now we're in the case where the self-touchings are something you like, and you can make the energy lower. And you have to prove that you can achieve a minimum of the Hamiltonian basically by a localized path. That is observation 1. It is not always known that this minimum would be unique. Well, not even unique up to sort of trivial symmetries of the lattice, but that is not important for the proof. And then you have to show that if you want to go outside of this box, then you're going to have an energy that is considerably higher than the minimal energy. So you take a path that is folded inside, and you take a minimum path, and you say, if I want to go outside, I will be really doing so much worse than this minimizing path because the gamma is larger than beta, and therefore not staying in a box that is finite will be very severely penalized. Okay, so that is the idea of the proof, and there's folding going on, counting. So there's, as I said, a bit of geometry and a bit of combinatorics, and that is how Remco and Achim provided the proof. So in terms of the mean square displacement, which is a quantity that we are going to look at quite frequently because it's a good indicator of the path behavior, it is expected. So again, one should say here it's predicted in the terminology that Gordon said yesterday, that the mean square displacement will be like some exponent. So if I would put here this mean square displacement under the path measure. So this is the expectation under the Gibbs measure of Sn squared. Then we expect as n goes to infinity that this is something that will be given by some exponent. And what we have proved here is that this exponent would be 0 in this part of the space, and if it would exist, it would have to be at least 1 over d in the other part of your phase diagram. Now, on this line, there is there's very little progress except in one dimension. There's a paper by Remco Rachib and Wolfgang König settling what I'm about to say in one dimension, but in the 2 dimensions it's still open. Here it is expected that the exponent is going to be 1 over d plus 1. 1 over d plus 1. So in between the value 0 and the value 1 over 2d here. And this brings me back to the question that Ron was asking. If beta is equal to gamma, then this thing comes out, and you can look at the difference of the number of self-intersections and self-touchings, and there's a way to rewrite this difference into the local times of the path. So the local times of the path, we'll come back to that later, is you count how often a path visits a certain site. And for every site, you can say how often has the path been there. You can write then the Hamiltonian in a somewhat simpler form. And if you somehow assume that these local times would typically be flattish over a big box. You say, let's take a box of a certain size, n to the some power, and the power, the best power so it turns out you can pick is 1 over d plus 2, 1 over d plus 1, sorry. Then this function becomes sort of very simple, and you can then sort of guess where there will be a kind of crossover happening. And so you will find with that argument that if you try to squeeze something in a box that is smaller than n to the 1 over d plus 1, it becomes too expensive. And if you try to spread it out over a box that is larger than n to the 1 over d plus 1, that's also unlikely, and that somehow this thing is the right scale. But that is a heuristic argument, and there's no proof of that prediction.
There are logarithmic corrections.
Yeah, there are logarithmic. Yeah, I'm wiping these under the rug. So this thing here should be thought of modulo logarithmic terms. And these logarithmic terms do indeed come up at this critical value. Oh, well, yeah. Okay, I wrote down this formula here. Yeah. Okay. Yeah. Still the original definition, though, if there are 2 points that are next to each other but that are not next to each other in the polymer chain, then I would call this a self-touching. Yeah, right. But of course, the one-dimensional model is hardly something that you could use to model this polymer and the poor solvent, but mathematically it's an interesting model and a non-trivial model to look at. Okay. I now want to go on and see what more we can say. And I'm going to tell you about what is believed to happen inside this inflated phase. Here we have said everything that there is to know. Everything lives in a finite box. Finished, Bob's your uncle, and there's not much more you want to say about that. But here, we only have information about things being at least as big as n to the 1 over d, so what's really going on in this phase? And the next thing I want to talk about is that it is expected that this inflated phase is going to split into two subphases. One phase where you are really going to see the behavior n to the 1 over d, and a phase where you're going to see something that is really bigger than n to the 1 over d, and that there is going to be a separation between these two. And we are expecting that when we're going to sit somewhere out here, gamma is small and beta is very large, then we should have weakly self-avoiding walk type behavior. And if beta is very large, we should have self-avoiding walk behavior. And here we are expecting to see exponents that would belong to the self-avoiding walk, and they are not 1 over d, they're bigger than 1 over d. Well, we know that in high dimensions and in 1 dimension, and it's predicted in dimensions in between. Gordon explained yesterday that we haven't even proven that in dimensions 2, 3, and 4, but nevertheless, nobody doubts that. And let's talk about what we are entitled to believe. Okay. Okay, so let me draw a picture of that. I'm going to wipe this clean and say, what do we expect is going to happen? Well, we're going to expect that between these here there will be something that we would call the collapse transition. And what happens is that it is expected that there is a second critical curve that has an asymptote up to some critical value gamma c, such that if I'm in here, nu is going to be the 1 over d in the sense of mean square displacement, again forgetting about logarithmic correction terms, and that in this part here, nu is going to be the exponent that belongs to the self-avoiding walk. Okay, so in here, then, we expect that if you take a box of size n to the 1 over d, that you're really going to be sort of living on the scale of that box and basically seeing almost everything of this box. Whereas here, I really expect that I'm going to have this random coil behavior very much like a self-avoiding walk. Okay, now for the undirected model, we are not able to prove anything of this, but I can even continue telling you something more. At this critical line here, so at this line here, there will be another exponent that is in between these two exponents here, which is the collapse exponent, and this takes two different values. It's 4 over 7 in dimension 2, and it will be a half in dimension greater than or equal to 3. And this has been argued in the papers I'm citing here by Duplantier and Saleur and Seno and Stella. So it's again one of those things that nobody doubts that this will be true. This is the prediction, but this has not been proved mathematically yet. Now, if I draw a picture like this, I should really now restrict myself to dimensions 2 or higher, because in one dimension, there really is not this line anymore, because in one dimension, this is already the exponent 1, and you cannot get bigger than 1. So in one dimension, you really only have this phase transition line between localized and between something that would be ballistic. And there is nothing more to prove. So in one dimension, we're done. But in a higher dimension, there is this curve coming up that really has a separation between these two phases. Okay, this phase diagram has been supported by simulations, heuristic theories. There's absolutely no doubt that this is what is true, but we are really able only to prove this exponent here, and in this part, a lower bound for the exponent being 1 over d, and that's where it is for the moment. Yeah. 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 It will become more diffuse because the moment you go away, then you will become the self-avoiding walk, which we know will be inflated. But of course, we do know that the self-avoiding walk exponent becomes a half in dimensions 5 or higher, and even including 4 if you are not worrying about logarithmic factors. But these things have not been proved for this model. Bertrand, is there any reason to believe why it would be exactly diffusive in dimension d greater? Yeah, and mind you, you are sitting on a particular curve that's a highly non-trivial function of beta, this gamma critical beta. So, okay, so here is the phase diagram for dimension 2. I'll keep it on the blackboard. So that is what we believe it will be with the 3 types of path behaviors that correspond to localized, collapsed, and extended. So the 3 different phases. And if you look at this phase diagram, you say, well, that's already quite an interesting and rich phase diagram for such a simple model where you have penalties for self-intersections and rewards for self-touchings. Now, in the first lecture, I was talking about free energies. And the first tutorial was about how do you prove the existence of free energies, and it was done for a very simple model. And I explained in the lecture that if your Hamiltonian is purely attractive or purely repulsive, you can, with a little bit of extra information, well, you can prove that the free energy exists, and you can kick out infinite values with a little bit of control on your Hamiltonian. Now here is a model for which there is attraction and repulsion, and then subadditivity arguments typically do not work. So we do not know the existence of the free energy in this phase diagram. We do know that in the localized phase, it's actually minus infinity, but it should be finite. Well, it is. It will be finite below the curve, but we do not, well, we cannot even prove that it exists. There's, again, there should be no doubt about it existing, but even that, which is much easier than studying the path behavior, has not been proved. Okay. I'm now moving to the second version of this problem that I would like to talk about, and that is in order to try and at least attempt some understanding of this second phase transition, which we are unable to do in the undirected model, let's see if we can come up with an easier model that still has much of the same flavor, and let's see if we can get our hands on this phase transition curve. And what we're basically going to do is we're going to sit infinitely far out on the right and see how things, so beta is going to be very short, and we're going to see what happens as I cross the value gamma critical at beta is equal to infinity. So that's the thing that we're going to try now, but for a different model that is directed. And here is a model that I'm going to tell you about, and there have been later papers with variations on this model. So it's a model that was looked at by Richard Breck, Tony Goodman, and Stu Whittington almost 20 years ago. And they say, well, let's make our set of paths simpler. We're going to look at directed paths. Paths cannot backtrack. They cannot go to the left. They can only go to the right, up and down. They can never go to the left. I also want them to be self-avoiding. So it has to be a path that once it goes up, it has to go up, and then the only way it can either go up, and at some point it will turn to the right, and then it can decide to go up or to the right or down again. But if it takes a certain direction, it has to pursue that until it makes a step to the right. So this is a restricted set of paths. They are self-avoiding. And again, for this path, since I make it self-avoiding, the self-intersections are gone. I'm no longer going to consider those. And that corresponds, in fact, to saying you are interested in what is happening when beta is infinity, because beta infinity would completely kick out all paths that would make any self-intersection. So let's not put them in the first place. Then we don't have to worry about them. And in these paths, I can count the number of self-touchings. If the path makes one step to the right here and then races down in the opposite direction, it will make a number of self-touchings. And again, I could say I can give the path a reward for doing that because it's avoiding the space. It doesn't allow any space for this bad solvent to come in, and that should be good. So here again, I take a path of this type, and I can count how many self-touchings there are, and I can build a model that would describe that. So here is what the model will be. My set of paths is all paths that live on the this should be a D. I'm sorry. So in the D plus one dimensional space, and in fact I'm going to for the picture I'm just going to take D is equal to 1. So this will no I'm sorry, I'm saying nonsense. Sorry, no. This is my space. My path lives in 1 plus 1 dimension. This is the half space, and every monomer lives in this half space. I'm going to start at 0 again. I'm going to make the first step to the right. This is just for convenience. I could kick this out, but it's nice to do that because we can use certain concatenation arguments. And then the path can just each time go up, down, or to the right, and it has a self-avoiding constraint that it can never intersect itself. So this is the formal way of writing down the path space that corresponds exactly to these pictures that I was putting up here. So the first step always has to go to the right for convenience, and then everything that looks like that. And there is no contribution coming from the self-intersections because the path simply makes this equal to 0. And the Hamiltonian is going to be of exactly the same type as I had before when this is gone. And it counts the number of self-touchings as before. So this is the same formula as we have. And it's living on this more restricted set of directed self-avoiding paths. And again, the Gibbs measure is going to be the same as here, where what you obtain when you just kick out the self intersections because they are not there. Again, you have an energy where every self intersection is rewarded, and you put this into your Gibbs measure, and this gives you a probability measure on the set of such directed n-step paths. And this measure has the property that if you do not have self-touchings, you do not have such a big weight, and the more self-touchings you make, the bigger your weight becomes. So it's a distribution that is a tilting, an exponential tilting of the uniform distribution on that set of directed self-avoiding walk paths, such that you favor these self-touchings. And again, so I repeat, we are not having any self-intersections at all, so the beta is completely out of the picture, and it corresponds to us wanting to see what is happening very far out here as I change the value of gamma. And we are, well, in a directed version of this original model, and we are expecting and hoping to be able to see that if you raise gamma through some critical value, that you will see a crossover because you go from below the asymptote of this line to above the asymptote of this line. So if there is something like that, then it will give us, for this directed model at least, a feeling that something like this picture is indeed going to happen. Now, for this model, I can define the free energy. And because it's a directed model, I said in the undirected model, we do not know that the free energy exists. And here, the free energy, which would be, let me write that bigger, the free energy, which would be a function of gamma, would be defined as the limit of n going to infinity, 1 over n of the partition sum in the directed model. And I explained to you that if you have such an object, then looking at whether this object is differentiable or not, or non-analytic at certain critical values, will be an indication of a phase transition. I explained that at the end of the first lecture. So what we're going to try and do is we're going to compute this object, well, or at least we're going to get some sort of representation for it, and then we will try and see if there are certain values of gamma where this thing is non-analytic, and there will be a positive critical value at which this thing is non-analytic, and it's that critical value that we want to associate with that critical value over in that picture. So we will be looking for something, and we will find that there will be some critical value gamma that is positive, such that this phase will correspond to the collapsed phase, and this will be corresponding to an extended phase, and here F is going to be non-analytic. So it will be in that sense that we will be able to see that there is a phase transition coming up. Okay, and so here's the theorem that is known about this model. First of all, this free energy exists. The existence is not so difficult. I will say a bit more about that in a second. But because now we only have an attractive interaction. We have kicked out the repulsive interaction. We have a restriction on the set of paths. But because things are only attractive, you can use the more standard concatenation arguments and prove the existence. This free energy will also be finite. And there will be a non-analyticity at a value gamma c, which is the logarithm of a certain number, xc. And this xc is the solution of a cubic equation, the unique positive solution of this particular cubic equation, which happens to be approximately this number. So that will come out of a calculation that I will sketch for you in a second. And the collapsed phase will correspond to making the attraction larger than this gamma critical, and the extended phase when it is smaller. So basically what happens if I make the gamma larger than this particular critical value, the reward for self-touchings is so big that this thing is sort of going to fold onto itself, and it's mostly going to spend its time sort of being attached to itself. And the moment I do not make the reward big enough, that's not going to happen. It's basically going to be much more extended, and it's in fact going to have a smaller number of self-touchings. And we will make that more precise in a second. And the reason that you really need a strictly positive critical value of gamma is that the moment you collapse this thing, you lose a lot of entropy. The number of paths that does make many self-touchings is small. And so you have to make the reward big enough for this thing to really want to collapse, because if it collapses, it can only do so following a very small number of paths compared to the total number of paths. And you have to give that small number of paths a big reward so that they will really become dominant they will dominate the behavior. Okay, I'm going to very quickly go through now 5 steps of how you prove this theorem. And the details of that will be part of the tutorial this afternoon that Nicolas Peturis will give. So he will go into the finer details of this calculation, and that allows me to sort of go quickly through this and say, well, this is the kind of things that you do, and we will see in detail this afternoon how that works out. Your partition sum, which is the thing that you want to understand, yes? Yes, there are. Oh, yes. In this directed model, you can prove many things. You can say, for instance, how much it fluctuates in the these things are all doable. Yes.
So there's a difference in size in the two.
Yes. Yes, definitely. Yeah. So and you will see that when I come to what the free energy looks like. So the free energy, so the partition sum is this sum. You take the sum over all paths of e to the minus gamma times the number of self-touchings. And in order to understand how this behaves, we're going to introduce the following object. So this is very similar to the generating functions that Gord was talking about in his lecture. You pick any positive x and any positive n, and you say, let C and M be the number of n-step paths that have exactly m self-touchings. And then if I write e to the gamma as x, then I will be able to, sorry, this should be a plus. I'm afraid this should be a plus, I'm sorry. Then you can write your partition sum as this generating function. And so you have to count the coefficients of that object. Now, the existence can be proved of this limit using subadditivity arguments. And you don't have to worry about free energies blowing up, because there are not more than 3 to the n paths. So you can easily get an upper bound on the free energy that is a very simple function. So by very crude counting, things can never blow up. I think I have again here an error. This should be a plus, but okay, never mind. so this is this object that comes as this generating function. Let's also put in a generating variable y with respect to n, so to get a generating function in both variables, so the length of the polymer and the number of self-touching. So I will get some double generating function with x to the m and y to the n of this coefficient. The number of self-touching can never be more than the length of the polymer, so it would be an object like that. And this, you hope that if you can compute this object, that you would be able to say something about the free energy, because if I would be able to compute this object for every x and y, now x is e to the plus gamma, and if I would be able to see where this starts to blow up at a particular value of y, then I would be able to catch what the exponential growth rate of this object would be, and that is exactly what the free energy is going to be like. So looking at when this thing for different values of x is going to blow up as a function of y should be able to identify as what the free energy is as a function of this new variable x, which I've put e to the gamma. And here's the key lemma that comes out of a longer calculation, that you can set up a kind of recursion scheme between these coefficients c, n, m. So you can express c and m in the same object with smaller indices, and you put this all into a generating function, and this will give you a relation for your generating function, which you can solve. And it turns out that the generating function has this shape. It's basically, apart from two very simple functions, a ratio of various objects. Now, a and b are certain polynomials in x and y that come from the underlying combinatorial structure in the problem. Then there is a function h, which is a ratio of two what are called Q hypergeometric functions. They are sort of looking a little bit frightening here, where there's two of them with r is 1 and r is 2, and the r dependent sits here and sits here. And the Q parameter is, the important parameter here is x times y. And so this is perhaps a frightening looking object, but it's also an object that has a combinatorial structure that you can deal with. In fact, earlier in the school, there was a series of lectures by Philippe Di Francesco, and at the very beginning of his course, he was talking about counting certain paths with geometric constraints, and well, he was talking about many different examples, and somehow this is an animal that lives in that zoo. So it has a very combinatorial background. Yeah? 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 Let's see. No, the 1 is here already. So you could say, why am I putting the 1 here? Well, that's because there are also other functions around, but the 1 is always. So, can you say that again? I'm missing the point.
So H is the ratio of G01 and G11?
Yeah.
And then you're defining GR1 for R equals 1 and 2?
Yeah. Oh, no, that should be 0, 1. Thank you very much. That is really a stupid typo. Sorry. Yeah. Yes. No, it should be R is equal to 1, and then this should be 1 and 2. Sorry. Okay, now this quotient of Q hypergeometric functions can be analyzed in detail. It's not something that is that easy, but you can sort of you can link these objects to certain continued fractions, and the continued fractions are nice enough to to be able to analyze. And continuous fractions are also wonderful if you want to do something numeric, because they typically converge very fast. So you can do good analysis on this. And what will happen, and this last part I will put in a picture in a second. We were interested in, so x is a function of our parameter gamma, e to the gamma, and we wanted to know for what values of y, depending on x, this is going to blow up, because that would indicate how the exponential growth rate of the free energy. And you can do that, and there is a certain critical curve, x going to ycx, where that blow up is actually happening. And then that curve will exactly tell you what the free energy is, because the free energy will be exactly minus the logarithm of the value of the critical curve at the value of x that parameterizes gamma. So once I know the curve as a function of y as a function of x, where this thing starts to blow up, then I know how my free energy behaves as a function of gamma. And here's a picture of that. Remember that Q is 1 was a typical thing here. So it turns out that there is a hyperbola, x, y equal to 1. So this corresponds to Q being equal to 1. And the critical curve for a while lies on this hyperbola, and then it sort of branches off at a certain value xc, which is exactly the xc that appeared in the theorem. And therefore, this xc is supposed to be linked to our critical value, where you say here you are in one phase, and the free energy takes a certain value which is related to what the value of this curve is. And then here you branch off, and here you get into another regime, and the phase transition, therefore, is linked to that. So the gamma critical is such that this particular x critical is e to the gamma critical. So that's how you get it. And this is so this afternoon, Nicolas is going to explain more about the background of these computations. So I can now draw you the pictures of the free energy and also the derivative of the free energy that come out of this. And the free energy looks like this. Now we're going to be back at the gamma language, and it turns out that you will see that it hits a linear line here above this gamma critical, which is given by the log of this number xc, and below it, it will level off like this, and it will actually have an asymptote which would correspond to gamma even becoming negative. So that would mean that I would start to give a penalty to self-touchings. And so in this regime, the penalty is so severe that the path doesn't want to have any self-touching at all. And so basically what you see here is the residual entropy of the set of paths that try to avoid having self-touching altogether, because here in this regime they would be severely penalized. But the interesting part for the collapse transition is happening here. Yeah. So the value at 0 you can compute. It's just the entropy of this set of paths, which is a simple number. Yeah. And if you take the derivative of this free energy, then it reaches the value 1 above gamma critical, and it will be smaller below that. And this is an indication of what Chuck was asking. So if you are below, so if your gamma is above critical, you will sort of collapse onto yourself. The fraction of time that this polymer spends self-touching itself will be asymptotically equal to 1. So what you will see is that it's all the time going next to itself. It has almost maximal number of self-touch. Occasionally it will, it does still have some fluctuations, but it's spending almost all of its time touching itself. And below the critical value, it doesn't do that all of the time. There will be a positive fraction of time that it does self-touch itself, but it will not be maximal. And in this regime, it starts to be really moving away from itself because it doesn't have to touch itself all the time. And these are curves that you can hammer out to any detail that you would like. You understand the qualitative properties and everything. And again, at the end of the first lecture, I was explaining why looking at the derivative of free energies is a very important thing to do. There where free energies fail to be differentiable, in this case they fail to be twice differentiable, you will see that something interesting is happening that is associated with a phase transition. Okay. I am now coming to the third and last part of the talk. And in the remaining 10 minutes or so, I want to tell you about a model that Dima was talking about in his evening talk last night. And that is a very interesting model where you say, well, what happens when I take a collapsed polymer and I try to pull at its two ends? Or I could sort of stick one end at the origin and I could start to pull at the other end and say, if you are collapsed, can I, by pulling on you, can I decollapse you? And as Dima explained, the undirected model is very hard to look at. That's what I've been talking about in the first part. But if you start to pull on this thing, you can still get your hands, even in the undirected model, on something interesting, namely this transition of trying to decollapse it by pulling at it. And you can look up a paper that has just appeared in the Brazilian Journal of Statistics and Probability by Ivan Velenik and Dima this year. And I should also mention the earlier work on this by Martin Zerner 10 years ago on this problem. So let me repeat what the model is all about. I'm having a Hamiltonian that has an interacting part. So this would be something of the type that we have so far seen before, and I will make, and it's controlled by a certain function psi. And there is a part that comes from pulling at the polymer. So the path is ending at position Wn. So now this is again the old space where there's no directedness or what's going on. It's the set of all allowed possible paths. And if I apply a force phi, which is a vector, to the endpoint of the path, then phi Wn is the work that is exerted by the force to move the endpoint to position Wn. So this is the energy that I am subtracting, let's say, from the polymer by applying this force. And then there are various choices that you can make for this psi. It will be a function, some function of the integers, and it will be a function of the local times of the paths. So I can pick a certain path W of length n. I can ask how often does that particular path visit a site X. So this will be a family of numbers, integer numbers that I assign to the various sites of X. And those will be called the local times. The sum over all x of ln x is just going to be n plus 1. That's the total number of times I jump to a point. And I can make the interaction such that it will look locally at how often I visit a site and will give a certain energy depending on that. So at every site, there is some sort of energy going on, which will be a function of the amount of time that I will be there over the course of time. Yeah. So for instance, if I would, so I'll come to that in a second. So, and then again, once I have given this Hamiltonian, I can define my Gibbs measure that sort of tilts the probability distribution. This is again the probability distribution of the simple random walk of length n on this set of unconstrained paths, and I tilt it by this particular Hamiltonian, and here's my partition sum. And there are two qualitatively different cases. There's a case where psi is growing faster than linear, and there's a case where it grows slower than linear. If I would make psi perfectly linear, it would not make any effect because the sum of the local times over all x is a constant. So a linear psi corresponds to having a Hamiltonian that doesn't really depend on the path. And the typical case here, for instance, would be that the function psi of L would be like L squared. So if I take psi to be beta times L squared, psi of L would be beta times L squared, where L would be this local time, then that corresponds exactly to the weakly self-avoiding walk, because Pn is the law of the simple random walk, so the one with no interaction. Oh, that's a typo. I'm sorry. This should be simple random walk. Very, very, very bad mistake. No, this is simple random walk. So if this is a square function, it corresponds to the self-avoiding, to the weakly self-avoiding walk. And if it's sublinear, then it corresponds to an attractive model. So you could have this by saying each time I visit a point again, I will give it a reward, but each time a somewhat smaller reward. So I come back to a site, I say you get a reward, but the next time you come back, I will give you a somewhat smaller reward. And this case can also come from a version of a model that I will discuss in lecture 6, which was also mentioned by Dima yesterday, namely I will discuss the directed polymer in random environment. And if you take an annealed version of that, you will get something that falls into this class if your disorder is positive. Just forget that remark, but for those of you who would understand this links back to what Dima was saying, because he was also talking about that model. Okay, and what happens in this model is something very interesting. So if you are repulsive, so superlinear, then you will always be in an extended phase. If you pull on the polymer just a tiny little bit, you will just make it move fast, ballistic. But if it's attractive, then you really have to pull on it enough to decollapse it. And there is a certain set that will depend on your interaction function that you choose that is non-empty and is convex and compact, such that if your force is in this set, then it's not strong enough to decollapse the polymer, and if it's outside this set, then it will decollapse the polymer. And here, collapsed phase and extended phase means something a bit different from what we have done in the model without force. This means your endpoint is not linearly far away from the origin, and this means it is linearly far away from the origin. And so it's a very beautiful paper. I would invite you to look at that work, because also it uses coarse graining arguments to say, even though we are having an undirected model, in this extended phase I can think of the model as sort of consisting of blocks, and these blocks I can think of as a kind of coarse grain directed model, and it's beautiful that we can get our hands on this problem. No, in this case, I'm talking about. I said, I mean, extended and collapsed here have a different meaning. This means sublinear, and that means linear. But I'm using the same names because I want you to think of it in analogy with the other model. But this, no, they correspond to these two cases. Sorry, the 1 and 2 correspond to the superlinear and the sublinear. Okay, so it's time for me to summarize what we did, and so I think it remains a main challenge trying to really make the details of this model precise, and that is very challenging because some part of it will be at least as difficult as understanding the self-avoiding walk. So this is a big challenge. I quickly mentioned here simulations that have been done for the undirected self-avoiding walk version. So the second model where I do make the model self-avoiding, but I do not. I do allow it to backtrack, and the simulations do coincide with what we are expecting. So our belief is not being shattered by the simulations at all. And here is this phase diagram, then again, that we want to look at. So there is a part that has been proved. Here we have a lower bound, and there is progress in this little quarter out here. In a paper with Remco and Wolfgang, we proved that if you would make the gamma and the beta very small as a function of n, then and you're sort of moving like this, then indeed you do get this kind of self-avoiding walk behavior, but at least in one dimension we found that. And there is work hopefully coming up by Roland Bauerschmidt and David Bridges and Gordon Slade in a finite neighborhood somewhere down here. Again, you're trying to understand this problem when you have a tiny little attraction attached to the repulsive model. And this, so far, well, they're looking at the 2-point function, not at the mean square displacement. But this will be in the spirit of some of the things that Gordon will explain in lectures 5 and 6. So I'm going to give you a take-home message at the end of every lecture. I will need 1 more minute to say that. We have looked at an interesting model where there's competition between attraction and repulsion. We found that for such a simple model, there are 3 phases possible, so quite a rich behavior. We looked at a directed and an undirected version. The directed model we just took because we wanted to be able to make some progress on the problem, and you will and you see that there is, even for such a very simple model, already such a rich phase diagram with lots of challenges if you want to put your teeth in that. Thank you very much. Yes, yeah. So there's a question, can you do what I was describing for the directed model in 1 + 1 dimension? Can you do it in 1 + d dimensions? Yes, you can, but these Q hypergeometric functions are going to become even a little more complicated. So in principle, you can do that. I don't think, I mean, I haven't seen a paper that does it, but I'm sure you can.